My name is Amelia, and this is the third lab for Physics 2211. In this lab, we will calculate the net force components from observing the motion of a star orbiting a black hole to determine the mass of the black hole. The results are as follows, where the mass of the black hole was determined by taking the mean value of all of the calculated masses values from the observed data. From Newton's second law, the net force can be broken down into parallel and perpendicular components. When we take the derivative of this formula, you get the updated formula below. The instantaneous rates of change of momentum can also be split into parallel and perpendicular components. The parallel component will always be consistent with the present momentum, which is representative of the change in magnitude of the momentum times the direction, or p hat. This indicates the dp/dt parallel will always only correspond to motion that is speeding up or slowing down, also known as a change in acceleration. The perpendicular component will always make a 90-degree angle with the present momentum, which is represented by the change of direction, or p hat, of the momentum times the magnitude. That indicates the dp/dt perpendicular will always only correspond to motion that is changing direction. Change in momentum is directly proportional to force, as indicated by Newton's second law, so when you add the parallel and perpendicular components, it is equal to the dp/dt, and therefore equal to the net force when you add net force times time to the present momentum. Here, I change the star's mass to the mass given in the lab instructions. In the while loop, the x-component's velocity is being calculated by taking the difference of the two corresponding data points and dividing them by the change in time between them, as the velocity formula equals the change in position over the change in time. The same thing is done for the velocity in the y-component, but then the gravitational constant was added, as well as the star's mass. The time interval was also indicated to be 1 day. In the next while loop, which ran until there was no more observed data points, the initial and final velocities were defined from those points, then the initial and final momentums were calculated from the definition of momentum, which is mass times the respective velocity. The change in the star's velocity and momentum followed the formula of the final minus initial respective values. dp/dt was indicated as the fundamental principles that say the change in momentum over the change in time, which was also set to equal the net force as determined by Newton's second law. From the fundamental principles, it was determined that in order to find dp/dt, the change in magnitude per time, along with the direction, needed to be calculated as p hat equal to the norm of the final momentum, and the change in magnitude of the momentum per unit of time was calculated as the magnitude of final momentum minus the magnitude of the initial momentum divided by delta t. When you multiply these two values together, and the parallel component of the dp/dt can be calculated. To calculate the perpendicular component of dp/dt, the formula of the parallel minus plus the perpendicular equal to the total dp/dt can be rearranged to solve for the perpendicular component, since Newton's second law states that the change of momentum can be set equal to the corresponding force components. In order to calculate the mass of the black hole, the gravitational law can be rewritten to be solved for the mass, where the mass of the black hole was determined by taking the mean value of all of the calculated mass values from the observed data. Here you can see the observed data and the results as given. The blue, pink, and orange arrows are as indicated and show the force in the net force of the parallel perpendicular forces acting on the star by the black hole. According to Newton's second law of change of momentum for change in time is directly proportional to the net force, so the two are equal to each other, as proven by the results in this lab. It can particularly be seen when in the code the net force components is set directly equal to the change of momentum components. If the star's motion stayed the same, but if the mass of the black hole has changed, you would not be able to determine the new mass as the original mass that was calculated from finding the net force from the motion observed. If the motion would have stayed the same, there would be no difference in the net force and therefore no change in mass.